All right, so let's get going on today's meeting. So what we're going to be doing this week for the next two meetings is we are going to start our look at confidence intervals. So confidence intervals are going to be the first real world application where we are going to use the ideas that we have been building up of the measure of the central tendency, the mean of a sample, standard deviation of a sample, and that distribution of sampling means that we introduced last time we met. We're going to put all those together to come up with a very useful tool that people can employ in the real world in order to make decisions, in order to plan projects, basically in order to not just go out on a hunch, but actually quantify how confident you are that you're going to be able to meet certain deadlines or have certain sized effects. Basically, it's a way of estimating where you can control how certain you are in your estimate. So this is going to be, we were building to it. This is going to be our first actual application of inferential statistics, where we are going to take data from a sample and then infer conclusions about, in this case, ranges of an estimate using the techniques that we are going to take a look at this week. So we're not going to see it explicitly, but just be aware that this is based not on the mathematics, but on the mathemagic of that sampling, that distribution of sample means. So we're not going to see it explicitly today, but just know that it is what underlies the ability to create these confidence intervals. And then we are also going to hand off the generation of confidence intervals to computer programs. We're going to be using an applet today. And then next time, we're going to see how to do the calculations if needed in Excel. So we're going to hand off some of these calculations because we are starting to get to a point where the calculations are still simple, they're still straightforward, but they do start to stack up where there's a number of different calculations. And anytime you ask a human to do very simple things many times in a row, the chances of a single error occurring increases. However, when you ask a computer to do many things, simple things in a row, basically it can get it right 100% of the time. So we are going to have a do it with me demo today, where we're actually going to start with a known population distribution. And again, this is something that we don't typically have, but for educational purposes, just so you can visualize what's happening, we're going to start with that. And then we're going to take samples from that population distribution, and we're going to build confidence intervals with this follow along, do it with me demo. All right, so this is going to be part one of confidence intervals. We are going to start very basic. We are going to introduce the idea of what exactly is a confidence interval. We are going to talk about the correct way to interpret a confidence interval because they are one of these statistical tools that oftentimes gets misinterpreted. And then we'll break down the confidence interval into its two components, specifically the point estimate and the margin of error. And then we're going to do a little bit of a deep dive into the margin of error, just so that we can see the factors that affect the margin of error, because you want your margin of error to be as small as possible. It's right there in the title. It's error. You don't want a big error. You want a small error. So what are the factors that actually affect the margin of error? And we'll take a look at the two that affect it: confidence level and your sample size. So what is a confidence interval? So this is from your textbook. A confidence interval gives a set of plausible values for a parameter based on sample data. So the two important things there is, first, it gives you a set of plausible values for a parameter. So a confidence interval is an interval. It is a set of values. It's not a single value. It's a set of values. It's a range of values for estimating a particular parameter, something about the population, something that we do not know because we don't have access to what the population actually is. And then I didn't bold this, but the second part that is very important for this is that it is based on sample data. And calculating a confidence interval, creating a confidence interval It is an algorithmic procedure where you start with sample data, data that you can actually measure, that you can actually hold in your hand, that we have access to. And through this algorithmic process, we create a confidence interval, and that removes any bias that we might have as humans. Because plausible values for a parameter, those will change depending on who you're talking to. So if somebody believes in a cause, the plausible values for estimating how effective that cause is will be completely different from somebody that doesn't believe in the cause and thinks that that cause will have no effect whatsoever. So plausible values will differ in terms of what our human biases can come up with. But when you base it on sample data and you use the confidence interval algorithm process that we're going to take a look at, then you can say with mathematical precision, getting the bias out of it, I can be 90% confident that this interval that I just gave you contains the parameter that you are interested in. All right, so let's set this up with a scenario. So in this scenario, there is a study, a psychology study that is going to be done. This is a rather large scale study. So in order to manage this study, Dr. Rivera, who's the principal investigator, she calls in Alex, and he's a project manager, and she's going to have him manage the phases of this study, which are the recruitment and the testing. So Dr. Rivera, in this scenario, she's interested in testing how acute social evaluative stress. So stress when you're evaluating your social standing in a situation, how acute social evaluative stress changes both visual attention and risk impulse decisions, and whether short-term cortisol reactivity predicts performance shifts. So does it affect your visual attention? Does it affect your risky impulse decision making? And does that short-term change in your cortisol reactivity actually predict these performance shifts? So that's the project that she is wanting to do. And it's a rather large-scale project. They're looking to recruit 600 eligible participants between the ages of 18 and 30 from across campus and the local community. Recruitment is going to be via an IRB-approved social ads, student listservs, flyers. The subjects will be will complete a pre-screen survey for eligibility, health exclusions, any visions, medications, or sleep issues. Eligible participants receive an online consent, then schedule a lab visit through a data collection platform. And then a subset of these individuals will receive mailed saliva kits, which is how they're going to measure that acute cortisol reactions. So that's phase one, the recruitment and screening. And then phase two, they're going to have in-lab testing. And in this case, the visit length is going to be about 90 minutes. So they're looking for 600 individuals, 90 minutes each. And they're going to do a stress induction, where it's a standardized mock job talk with a panel Q&A in a controlled room, so that induces a certain amount of stress. Then they're going to take biological measures like the saliva samples at baseline after 15 and 35 minutes. They're going to do an eye tracking phase of this, where they're given an attention task, and they have eye tracking that measures where they're looking at those particular times. There's going to be a decision task, which is the one to measure their risky decision making. And then afterwards, they're going to complete some questionnaires to measure their state anxiety, their perceived stress, their recent sleep, and recent caffeine and nicotine consumption. And then this will be followed by a debrief, full disclosure about any of the deception, and resources provided for the subject. So a rather large scale project. This will be funded by a government organization, most likely, and they're going to have a timeline under which they want certain results. So Dr. Rivera would go to the project manager and say, basically, this is what I would like to do. Here's my budget, and what timeline can we expect for this project? So Alex, the project manager at that time, would go back and to his team, and importantly, they would use data on similar projects. So this is an important thing to remember in this scenario. Alex isn't just coming up with numbers willy-nilly. He's actually going to prior projects that either he managed or maybe colleagues of his managed that had similar types of recruitment requirements, similar types of testing lengths, similar types of equipment that was used, similar types of universities. So you try to collect a sample of different studies that have already occurred, and then he's going to base his estimate on that sample of previous studies. So if you ever do get into the world of project management, there are many strategies that they use in order to kind of collect that sample and create the data that they need to base their estimate on. But that's not the point of today. All we need to know is that Alex goes away, does some work, collects data, collects a sample of previous projects that were very similar and looks at how long they took to complete. And then after that analysis, he would come back to Dr. Rivera and he would say, all right, this is what we have. We did the analysis for recruitment. We did the analysis for the actual testing. And we came up with the following confidence interval of our best estimate being 21 weeks. So the best estimate that they can give Dr. Rivera is 21 weeks. However, that's not a confidence interval. That's just the best estimate. The confidence interval is underneath, and it's a 90% confidence interval. And what it gives you is it gives you two values. It gives you your lower boundary and it gives you your upper boundary. So Alex would tell Dr. Rivera, based on the sample that I took, based on the data that I collected on similar projects, I can, with 90% confidence, predict that this study is going to take at least 18.3 weeks, and it's going to take at most 23.7 weeks. That's my confidence interval. So they don't know exactly how long it's going to take. His best guess is 21 weeks, and we'll talk about that in just a little bit. But he is 90% certain, based on his previous data and the building of a confidence interval, that the actual project will be completed between 18.3 weeks and 23.7 weeks. So that's the confidence interval. So why do we need this confidence interval? Why do we need an interval? Well, the reason we need the interval is because we're trying to predict how long this project is actually going to take, but we don't know what are the challenges, obstacles, things that are going to go wrong. What are the bonuses, fast tracks, things that go right? There are many things that can occur when you're planning out a project, which is why you hire a project manager to do a lot of this work. But there are many things that could occur that'll either speed up the process or slow down the process. And what Alex is telling Dr. Rivera right now is that regardless of what happens, regardless of what the future holds, he is 90% confident that their project will be finished between 18.3 weeks and 23.7 weeks. So he doesn't know what's going to happen, but based on previous history and what happened with other projects, this is the prediction that he can make. 18.3 is the low end, the lower boundary. 23.7 is the upper boundary. So far, so good? All right. So what happens? Well, we only live in one world. And if you recall previously, we talked about how sometimes in statistics, it's very helpful to think of what happens in different realities, what happens in different worlds. So in this case, we're going to take this confidence interval, this 90% confidence interval of 18.3 to 23.7 weeks, and we're going to see what happens to this interval. Is Alex successful at predicting this interval in 10 different scenarios, in 10 different possible realities? So I labeled these with Greek letters just to give it a little bit more gravitas. So what happens in world alpha? So this is one possible world that has its own set of problems, its own set of issues. And one of the days during the project, Alex walks into his office and he sees a note left on the whiteboard from one of his team members. And the note says, IRB clarification adds 2 business days New total, 21.3 weeks, Mary. So something has happened, something unpredictable. The IRB required clarification on some of the details, and this is going to add another 2 business days to the total. So the total now goes from, their best guess goes from 21 weeks. Now we add 2 more business days, so now it's going up to 21.3 weeks. So Alex seems a little worried, but he doesn't seem too worried because he can go back to Dr. Rivera and he can say, hey, our previous best estimate with 21.3 weeks, now we're on schedule for an updated estimate of 21.3 weeks. But notice, it's within the confidence interval. 21.3 weeks still falls between 18.3 and 23.7 weeks. So from a planning point of view, he has still successfully predicted how long this project is going to take. So that was world alpha. What about the next possible world? We'll go visit world beta. And in world beta, this is a different world. Same Alex, same project, but now a different set of random things that could occur. And in this world, Alex walks into his office one day and he sees a note on the whiteboard. And the note says, ad creative underperforms at launch. New total equals 21.8 weeks from James. So James was analyzing their ad performance and it just seems like they're not getting the traction that they were hoping for. So now they're going to add 0.8 weeks to the total because they're just lagging a little bit on the recruitment. So Alex is a little worried, but not too worried because he can go back to Dr. Rivera and he can say in this new world, hey, my previous best estimate was 21 weeks. Now it's actually going to take 21.8 weeks. We've encountered a slight delay. And again, notice that this does not impact Dr. Rivera's plans at all because the original confidence interval was 18.3 to 23.7 weeks. So we are still within that confidence interval. We've still successfully predicted how long this project is going to take. And now we visit the next world, world gamma. And in this world, Alex, a new Alex, gamma Alex, walks into his office and sees this note, 1 day campus closure, snow day, new total 21.2 weeks. So they are now in the testing phases and they couldn't test on that day because it got closed, the campus was closed. So that pushes them back an entire day. Their new total is 21.2 weeks. And again, not a problem because the confidence interval holds this new updated best estimate, this 21.2 weeks, still within that lower bound of 18.3 and that upper bound of 23.7 weeks. All right, world delta. Delta Alex walks into his office one day and he sees this note on the whiteboard, eye tracker recalibration needed, new total 21.1 weeks, and that's from John on his team. So again, another unpredictable event. Didn't know if it was going to happen, didn't know if it wasn't going to happen, but based on previous samples of how long these projects took, we'll notice that the best estimate now changes from 21 weeks to 21.1 weeks, still within that 90% confidence interval. So plans still do not need to change. Dr. Rivera still is on schedule. Nothing needs to be updated. They're still within that 18.3 to 23.7 week window. All right, next world, world epsilon. Epsilon Alex here, he seems a little bit more worried. And the reason he's more worried is because he walks into this note here, data collection platform suffers a breach, add 3.5 weeks, new total 24.5 weeks. So a data collection breach, a security breach, that is a very serious thing to occur. That's going to require the legal department to get involved. That's going to require the IT department to get involved. They're going to have to approve a new vendor. There's a lot of work. It's going to take a lot of time. That pushes them back 3.5 weeks. Their new total is 24.5 weeks. So now Alex takes this to Dr. Rivera and says, hey, you know what? Our old estimate was 21 weeks. Our new estimate is actually 24.5 weeks. So that's actually outside our 90% confidence interval. This is the first time something happened that took them outside of that upper bound, in this case, 23.7 weeks. So this illustrates that your 90% confidence interval gives you 90% confidence that you're going to fall, whatever happens is going to fall within those boundaries, but it does also allow for 10% of the time for you to fall outside of those boundaries. So that is actually, I chose 90% because those are actually the confidence intervals that project managers do use. They will give you typically a deadline that'll work 9 out of 10 times. And in this case, unforeseen circumstance, data breach, actually pushes them outside of their confidence interval window. So that was Epsilon Alex. We now go to another world. This is Zeta Alex. And Zeta Alex sees that the no-show rate ticks up 5% for 2 weeks. That pushes them back, new total 21.6 weeks. But again, in this case, not a problem because their updated total still within that confidence interval. Down in world Eta, we have scheduling conflict for 2 rooms, for 2 of the lab rooms, new total 21.4 weeks. Again, not a problem because their updated best estimate is still within that 90% confidence interval. In world Theta, I don't know why he's looking worried in this one because a press mention actually boosts the sign up for a week. The new total is 21.3 weeks. So they got mentioned in the press. That actually boosted the recruitment. It boosted the speed at which they were able to recruit individuals. So now their best estimate actually goes down. Now it's still within those 20.3 weeks, but this is an interesting case because confidence intervals, when we report them, we always report a lower boundary and an upper boundary. So confidence intervals, as we're going to see very soon, are symmetric. There's always the one side and an equally large other side. There's like a mirror image to every confidence interval. It's symmetric. However, in the real world, we're usually only interested in one side of that confidence interval. So Dr. Rivera here would be ecstatic if the confidence interval was incorrect, but it was incorrect on the lower boundary. So if Alex came in there and said, hey, you know what? Something happened, it was unexpected, and we're now going to finish this project in 15 weeks instead of the 18.3 weeks. Dr. Rivera would be over the moon. She'd be like, oh my gosh, that is the greatest news I've ever heard. So usually you're only interested in one side of the confidence interval, but don't let that take you away or let you forget the fact that confidence intervals, as we see, are always symmetrical. There's always 2 sides to a confidence interval. You never just report the one side, even if the one side is all that you're interested in. All right, and let's finish this off. World IOTA. IOTA Alex comes in and it goes, software update causes a 24-hour glitch. I think we've all been there. New total, 21.2 weeks. Again, not an issue. Goes in to talk to Dr. Rivera and says, you know what, we got to update our timeline, but we're still within that 90% confidence interval. And then finally, World Kappa. Alex walks in, Kappa Alex walks in, and the saliva kit shipment arrives, but it's 4 days late. So that pushes them back 4 days. Their new total is 21.2 weeks. And this again, 21.6 weeks. And this again is within that 90% confidence interval. So let's take a look at what happened in this scenario, just as a brief synopsis. So we visited 10 different worlds where Alex came up with a confidence interval to predict how long was that project going to take in that particular world that he was in. And in 9 of those worlds, things happened as they often do. Actually, I shouldn't say often, as they always do in a project. Things happen, you go off schedule, but the confidence interval covered those off schedule unexpected delays. The confidence interval upper boundary and lower boundary still contained those delayed estimates even after those things happen in 9 of the 10 cases. And it was only in that data breach where the confidence interval was violated and the new estimate, the updated best guess, was outside of the confidence interval. It went beyond those 23.7 weeks. So this is what is meant by 90% confidence interval, is that 90% of the time you're going to be in a world where that confidence interval contains the parameter that you're interested in. In this case, how long is this study going to take? And only 1 out of the 10 worlds that exist in that multiverse is going to be outside of that confidence interval. So you have a 90% chance of being one of the green Alexes, and you only have a 10% chance of being the red Alex. And that's the idea behind a confidence interval. Any questions on that? All right. So how do we interpret a confidence interval? Well, to interpret a confidence interval for an unknown parameter, and again, these are unknown parameters that we're trying to estimate. If we knew what the parameter was, we could just be exact. So if Alex could somehow see into the future and realize that the project was going to take 21.7 weeks, he could come back to Dr. Rivera and say, I'm the greatest project manager in the history of project managing. I know exactly how long your project is going to take. But it's an unknown parameter. So we have to give it a confidence interval. And what we say is, we are C% confident that the interval from lower boundary to upper boundary captures the parameter that we're looking for, the parameter in context. So that again is from your textbook. We are C% confident, that's your confidence level, that the interval from the lower boundary to the upper boundary captures the parameter in context. So in that meeting, when Dr. Rivera, who at her stage would have taken a stats course, she knows what a confidence interval is. But let's just say that they're filming a reality TV show and they got to let the audience in on it. Alex would say, hey, those numbers that I gave you, 18.3 to 23.7, we are 90% confident that the interval between 18.3 to 23.7 weeks captures the timeline of the study. So again, they don't know what the timeline of the study is, but they are 90% confident that whatever that timeline is going to be somewhere between 18.3 to 23.7 weeks. Now notice, one thing to remember about confidence intervals is that your confidence interval is predicting the timeline of the study. So you will come across people who say that there are certain ways to interpret a confidence interval, there's certain ways to talk about a confidence interval. And typically the correct way is to talk about it in a sense that what you're trying to estimate doesn't move, but your confidence interval might move. So the timeline of the study, that is set in stone. Whatever world this is in, that timeline of the study is set in stone. But they are 90% confident that the interval that they have is going to cover whatever that timeline is. So it's almost like throwing a net out into a random sea, and you are 90% confident because of the size of your net that you're going to capture whatever it is that you're trying to capture. In this case, the timeline of the study. So I'm just saying this because in the textbook and when you read about confidence intervals, some people are really highly sticklers for saying that, well, you need to talk about a confidence interval like this and not talk about it like this. Really, the only thing that you need to remember is that what you're trying to estimate does not move. And your confidence interval has, in this case, a 90% chance of wrapping itself around that parameter that you're trying to estimate, that parameter that does not move. All right. Hopefully that didn't confuse you even more. But if it did, we'll go forward. I think when you see confidence intervals, you'll know more about what I was trying to say here. So confidence intervals, they're two numbers. There's two different ways to report them. We've seen the one where they report the lower boundary and the upper boundary. And that hides the two components of a confidence interval. So let's unpack that idea of what a confidence interval is actually made of. And a confidence interval is made of two things. It's made of your point estimate, and then it's made of your margin of error. And your point estimate is a single value estimate of a population parameter. A point estimate is usually what you get when you ask people to guess a particular population parameter. So if you walked up to somebody and said, what do you think the average height is of males in North America? What they're going to give you is a point estimate. They're going to say something like, well, it's probably 511, right? That is a single point, single number. That's your point estimate. Your margin of error, on the other hand, that's an estimate that describes how far, at most, we expect the point estimate to vary from what we're trying to predict from that population parameter. So the margin of error, it's kind of like just there on the tin. It's how much error can we expect around that point estimate. And that idea of it being around the point estimate means that your point estimate is the midpoint of your interval. It is the dead center of your confidence interval. And then your margin of error is the distance from your point estimate from the middle to the end points of your interval. So that margin of error tells you the distance from that middle point of the confidence interval to your endpoints of the interval. On the one side, plus, and on the other side, a minus. So let's go back to Alex and Dr. Rivera. So when we were talking about this and we talked about, well, the 90% confidence interval is 18.3 weeks, 23.7 weeks for the upper boundary, and your best estimate is 21 weeks. That best estimate, that is your point estimate. So if Dr. Rivera said, you know what, I got to go into a meeting with a bunch of administrators and educators, and I don't know if they've taken statistics. I don't know if they're going to understand a confidence interval. What is your best guess? I got to go in there and just give them one number. What's your best guess for how long this project is going to take? In that case, Alex would say, well, my best guess, that's 21 weeks. And that is the midpoint of the confidence interval. So if you actually take the average of 18.3 and 23.7, your upper boundary and your lower boundary to find the middle, you'll see that that's 21 weeks. That is your point estimate. That is the midpoint of the confidence interval. So that's your single value estimate, your point estimate, that midpoint. And then your margin of error, that's the distance from your point estimate to the end points of the interval. So in this case, we have a margin of error, and we can figure it out by starting at our best estimate, our point estimate, which is 21 weeks, and then seeing what the difference is between the lower boundary and 21 weeks, or, because it's symmetrical, the upper boundary and 21 weeks. And you can see that 21 weeks plus 2.7 weeks gets you to 23.7 weeks, your upper boundary. 21 weeks minus 2.7 weeks gets you down to 18.3. That's your lower boundary. So Alex, if he was answering Dr. Rivera's question about, hey, what's the margin of error on this confidence interval? He would say, hey, the margin of error is plus or minus 2.7 weeks. That's how much we expect the estimate to vary. So it could vary higher, it could vary lower, but on average, that's what we're expecting the estimate. That's how much we expect the estimate to vary. So to just kind of give you a visual of this, these are the components of your confidence interval. So we have a point estimate there in blue, and then we have a margin of error in purple. Margin of error to the left, that's the margin of error that goes lower. Margin of error to the right, that's the margin of error that goes higher. So for this project, for Dr. Rivera's psychology study, we have a point estimate of 21 weeks. And then we have a margin of error on the one side of plus 2.7. And then we got a margin of error on the other side of minus 2.7. And that point estimate with those margins of error give you your lower boundary of 18.3 weeks. And they give you your upper boundary of 23.7 weeks. So these are the components of your confidence interval. And just so that you don't get surprised when you see this, confidence intervals are typically reported in two different ways. Whoever's reporting a confidence interval typically chooses just one of those ways. So sometimes you'll see it reported the way that Alex reported it here, with just a lower boundary and an upper boundary. And he'll say the 90% confidence interval, lower boundary 18.3, upper boundary 23.7. that's your 90% confidence interval. Other times it's reported as your point estimate and your margin of error. So Alex could have said, hey, the 90% confidence interval, 21 weeks plus or minus 2.7 weeks. So sometimes you'll see it one way, sometimes you'll see it the other way. It's the exact same information, just reported in two different scenarios or two different formats. All right. So now that we know the pieces of the confidence interval, now that we know the point estimate and the margins of error, we're going to wrap up today by doing a deep dive into the factors that affect the margin of error. Because you can imagine what you want in your confidence interval is for those margins of error to be as small as possible. Because it would be way more useful to Dr. Rivera if Alex came in and said, hey, my estimate is 21 weeks plus or minus 2.7 weeks. That's way more useful of a confidence interval than for him to come in and say, hey, my estimate is 21 weeks plus or minus 17 weeks. So anywhere between 38 weeks all the way down to 4 weeks. That's what I'm 90% confident in. That's not a very useful confidence interval. So we're trying to get that margin of error down. So what affects the margin of error? Well, there's two things that affect it are your actual confidence level and your sample size. So to see this in action, we are now going to do a do it with me demo. So if you haven't already, highly recommend so you can follow along. Go to staplet.com/confint.html and open up this simulator applet here. So this is going to be simulating confidence intervals, and we will just reset everything here so we can start together, and we're going to build up confidence intervals. Now, what we're going to do first, just once again to drive home the idea, number one, that populations are often not normally distributed. So this first distribution here, this first distribution curve here, this is your population distribution. Most of the times this is unknown to you. So this is just for educational purposes that we have this omniscient view of the population distribution. But just to kind of drive home the idea that these techniques do not require your population to be normal, we're going to start off with a skewed population here. And again, we wouldn't typically know that it's skewed, but because confidence intervals work their way through the distribution of sampling means, and because we know that the distribution of sample means is normally distributed, regardless of what your population is, we're going to start with a skewed just to kind of drive that point home. Your population does not have to be normal. So we have a population parameter of 3 for the mean of this population. That would be what we're trying to estimate. So we're going to try to estimate the population mean. So typically we wouldn't know this. We wouldn't know it's 3. We know it's 3 now for this demonstration. And we're going to keep this the way that it is right now. We're going to select one random sample of size equals 30. And we're going to compute a 95% confidence interval. And then we're going to compute the interval for the mean of the population. And we're going to use what's known as a t-distribution. And we're going to talk a lot more about what a t-distribution is next time. Just know that it is another bell curve that happens all the time as well. So just the way that the normal distribution often happens for a population, the t-distribution, as we're going to see, is the correct distribution to use when you're dealing with samples in an unknown population, but more on that next time. So we have that random sample size of 30, 95% confidence interval, by far the most popular confidence interval. And then we hit go here. And the first thing that you see is that this is your sample distribution. So these are 30 dots that came out of this population here. These are 30 dots over here. And with these 30 individuals that created a sample, we have a sample mean of 3.685, and we have a sample standard deviation. And then it actually computes a 95% confidence interval based on that sample mean and based on that sample standard deviation. So just a spoiler, sample mean and sample standard deviation, those are two of the numbers that we are going to need when we calculate these next time, and I'll show you how to do that. But on today's conceptual, what is a confidence interval day, we're just going to concentrate on what actually happened. And for that, we're going to scroll down here. And this is going to illustrate the success of the confidence interval. So this dotted line right here, this is the population parameter that we are trying to estimate. And this dotted line right here is at a value of 3. And the reason it's at a value of 3 is because the mean of this sample is, the mean of this population is equal to 3. So this dotted line represents the mean of the population. And then here we have a confidence interval. And the confidence interval is being reported here as a lower boundary and an upper boundary. And what that means is that this line here goes all the way down to 2.672, and that's the value right here. And it goes all the way up to 4.698, and that's the upper value here at the end of this portion of the interval. And importantly, this point right here, that is your point estimate. That is the center of the interval. And just as a kind of a spoiler for what we're going to be doing next time, that point estimate for any confidence interval is your sample mean. So your sample mean from a population is always your best guess for what is the mean of that population. So that forms the center of our confidence interval. Now, importantly here, we can see that this confidence interval, this one is in green. And the reason it's in green is because within its lower bound and its upper bound, the population mean is inside of those two boundaries. So we created this 95% confidence interval, and the actual population mean is 3, but 3 is within this confidence interval. So you can see that this dotted line falls within the confidence interval. So we have successfully predicted or estimated, not predicted, we have successfully estimated what the population mean is with this 95% confidence interval. So we're going to go down here now to quickly select, and we're going to change this 100. Let's just change it to 1. Let's just change it to 1. There we go. So we're going to change that to 1, and we're going to just continue to build or continue to take new samples and build new confidence intervals. So we're going to hit go here, and you can see that this confidence interval has moved. And the reason that it's moved is because we have now taken a new sample from this population, and that new sample has a new sample mean. In this case, it has a sample mean of 2.5. So that center point of this confidence interval is now 2.531. Again, that's our best guess. Due to the standard deviation of the sample, the confidence interval now is a little tighter. You can see that it's not as big as it was before, but importantly, it still contains, within its lower boundary and upper boundary, it still contains the value 3. It still contains that population mean that we are trying to estimate. So we can now continue to do this. So we can quickly select another sample. And you can see now that the confidence interval has actually expanded once again. This time, well, this is actually a sample that came super close to actually being exactly having the mean the same as the population mean. But we can just keep doing this and generate sample after sample after sample. And I wanted to get to one of these, and it actually popped up a little earlier than I expected. For this confidence interval, this one is in red. And the reason it's in red is because the interval, as estimated from this sample that we took from this population, we calculated an interval, and this time the upper boundary only goes up to 2.775. And it missed that population parameter. We were unsuccessful at estimating the actual population mean with this confidence interval. So now we know that the green confidence intervals, those are the ones that are hits. Those are the ones where the population parameter that we're trying to estimate is within the interval. The red ones are misses. Those are the ones where the population parameter is outside of the interval and we were unsuccessful. So now what we're going to do is we're going to go down here and we're going to change that one. So where it says quickly select, we're going to change that one from 1 to 100. And recall that we are creating 95% confidence intervals. So we are now going to quickly select 100 random samples. And for each random sample, we're going to calculate a confidence interval and we're going to graph all 100 here. And what we should find, if there are 95% confidence intervals, is that if we do 100 of these, we're going to be correctly predicting or correctly estimating, I keep saying predicting, correctly estimating the population mean around 95 times, and we're going to incorrectly estimate the population mean. We're going to miss it about 5 times. So let's hit go. All right, so these are the 100 confidence intervals that were just generated, and we can count up how many we missed. We missed 1, 2, 3, 4, 5, 6, 7, 8. So we actually missed 8. So 92 out of the 100 times we correctly estimated the population mean. 8 out of the 100 times we incorrectly estimated the population mean. So that was for a 95% confidence interval. And as you can see, we got pretty close to 95%. And if we were to quickly select not just 100, but 10,000, well, then that number just keeps getting closer and closer. This is a bit of a mess here. But importantly, that number just keeps getting closer and closer to 95%. So I don't want you to think, we'll clear those samples. I don't want you to think that the confidence intervals were calculated incorrectly. It's just by chance we ended up with 8 instead of 5. But again, the idea is that you have your sample, that's your midpoint, the sample mean is the midpoint, and then you calculate the margin of error around it. And with a 95% confidence interval, 95% of the time, you're going to hit or correctly estimate that population parameter. All right, any questions on that idea yet? So far, so good? All right, so let's get 100 samples back up here for display. So there are our 100 samples. And then I mentioned that what we wanted to see was, well, what affects the margin of error? What affects the margin of error when you're dealing with confidence intervals? And the margin of error is the arms of the confidence intervals. So the point is the point estimate. The margin of error is represented by the arms of the interval. And what we can do to see how that is affected, I'm going to just zoom out of here just a little bit. We can go up here and we can ask this applet to actually compute a different confidence interval. So we can say, well, hey, wait a second, you wanted it to be 95%. My partner wanted a 95% confidence interval, but they just worry too much, right? Well, they just worry too much. I like to gamble. I like to just kind of throw it to the wind. You know what? Give me like a 75. So if we change this to 75, and then we just hit enter, notice what happened to the confidence intervals. They all shrunk, right? Because when you decrease the confidence of your confidence interval, you don't have to go as wide to be sure that you actually capture that population parameter. You can actually shrink your margin of error. So the smaller you make your confidence interval, the smaller you make your confidence, the smaller your margin of error needs to be, the smaller your confidence interval. So this, you can actually also just increase this manually. So as we go up, you can see that the confidence intervals get wider and wider and wider. And as we go down in confidence, you can see that the confidence intervals get narrower and narrower and narrower. And you can see how much it actually increases as you go from really high confidence to super high confidence. you can see the jumps are a lot higher. And I think if I go to 99.9, you got to go really, really wide. So this again would be, just to put it back in that scenario of that project manager, if Dr. Rivera said, hey, you know what, I'm kind of laissez-faire, I'm sort of, I just go with the flow, give me like a 75% confidence interval. Alex might say, oh, okay, well, 21 weeks is our best estimate. I'd say somewhere between 20 and 22 weeks, right? I'm about 75% confident we'll get it done in 20 to 22 weeks. But if she had a nervous collaborator and that nervous collaborator said, no, I need 95, then Alex might have to say, well, okay, anywhere between 17 to 25 weeks. And if that collaborator got even more nervous and said, no, I need 99, then Alex would have to make it even wider. And if he said, no, I need 99.9, I need to know that only once out of 1,000 times are we going to not estimate this deadline correctly. Well, Alex can do that, but it's going to be a massively wide confidence interval. It's going to be something like, well, okay, it's going to be somewhere between 35 weeks and 6 weeks. That I am 99% sure that we can get between. So the first thing that you can see that affects the margin of error is your confidence level. And basically, if your confidence level decreases, you need a smaller margin of error, and you can see those confidence intervals decreasing. And if you want them to increase in confidence, you need a wider confidence interval. And I'm just going to try this. I haven't tried this ahead of time, but I think if you put in 0%, it won't let you do it. But if you put in 0.01, see how low we can get it. You can see that it goes down to just the points. And again, your point estimate is your best guess, but this illustrates the idea that your point estimate is almost always wrong, right? So if Dr. Rivera told Alex and said, hey, I need to know exactly how long this is going to take, Alex would say, hey, my best guess is 21 weeks, and I guarantee you that's wrong. Because it could take 21 weeks, or it could take 21 weeks and 2 days, or it could take 19 weeks and 5 days, or it could take 21 weeks and 20 minutes, right? Like you can't get that confidence interval down to a point. Because if you have a single point, you lose your margin of error. If you lose your margin of error, you completely lose your confidence. All right. Whoops. Wrong one. Okay, so going back to our little synopsis here. So the first thing, factors that affect margin of error. If your confidence level increases, your margin of error increases as well. So you want a bigger confidence level, you need a wider margin of error. You have a smaller confidence level, you have a smaller margin of error. So that was the first factor that can affect your margin of error. Now let's take a look at the second factor, which is your sample size. So we go back to the applet here, and let's get something that is reasonable again. So let's go for a 90% confidence interval. So we have our nice 90% confidence interval here. We have 100 random samples. And again, we have our skewed population distribution. But this time, what we're going to do is we're going to mess with the sample size. So we're going to start off with a sample size that is smaller. So let's say that instead of having a sample size of 30, we only had a sample size of 10. All right, so let's say, just to kind of put it back in the context of the project manager, let's say that Alex says to his team, okay, we got to dig up data on similar projects that we worked on or our colleagues worked on and base our estimates on that. And they come back and they say, hey, we found 10 projects that we've done before that we have data on. That's your sample size of 10. And when we put in a sample size of 10, pay attention to what happens to the size of these confidence intervals. So as we hit enter, they all disappear. Let's go right there. All right, so you can see that these confidence intervals, based on a sample size of 10, are much, much wider. So when you have a smaller sample, in order to maintain the same confidence level, because you're basing it on less data, you need a wider confidence interval. So with only 10 studies, with only 10 projects to take a look at, Alex would have to give a much wider range for his estimate in order to have that 90% confidence that they are correctly estimating how long the project is going to take. But you can see that as that sample size increases, so I'm going to increase it one by one, pay attention to what happens to the size of these confidence intervals here. Apparently it doesn't do that. All right. So as you increase it, let's just get 10 back. All right, so that's for 10. Let's increase it to 20 and we'll do 100 samples. So you can see when you have a sample size of 20, it is much, much tighter. And you can see now if we go back to that sample size of 30, much, much tighter. And if we get a sample size of 90, much, much tighter. And this is why you want your sample size to be as big as possible. Because when you have a larger sample, that margin of error goes down. Your confidence level gets tighter and tighter and tighter for the same level of confidence. Note, very importantly, we have not changed the fact that this is a 90% confidence interval. That has stayed the same. And when Dr. Rivera is done her study, and she has 600 subjects in her study, and she has 600 pieces of data, and they ask her, well, can you predict the confidence interval for risky decision making? Can you predict how risky a decision is going to be with 90% confidence? She's going to be able to say, well, my sample size is 600, so I can create a 90% confidence interval. And if we hit go here for a sample size of 600, you can see that that margin of error is super tight. And you can get a very, very tight estimate and still be confident that you're hitting that population parameter. All right, so to sum that up, in terms of sample size, as your sample size increases, your margin of error actually decreases. So if you want to have a small margin of error, you need to have a large sample size. And if you want to have a small margin of error, you need to shrink down your confidence level. Now, usually we don't want to shrink down our confidence level. And that's why psychologists who do studies always, always, always try to get larger samples, larger samples, larger samples. Nobody almost ever says no to larger samples unless they've run out of the money needed to analyze them. Because the bigger your sample size, the smaller your margin of error, the tighter those confidence intervals are. All right, so that was what I wanted to cover today. Any final questions on this intro to confidence intervals? Okay, so we talked a lot about how confidence intervals work, what they are, what they're made of. Next time that we meet, we're going to see how to actually get these numbers. So how do you end up with that number 21 weeks? And then most importantly, the trickiest part of it, how do you get that plus and minus 2.7? That's what we're going to see next time when we take a look at how to actually calculate confidence intervals. But today's goal is just to figure out what confidence intervals are. So hopefully you got a better grasp on that. And that's what we wanted to cover for today.